Welcome to the talk, Hardware Attacks, Advanced ARM Exploitation and Android Hacking, delivered today by one of the co-authors of the book Android Hack Handbooks, and also a regular speaker and trainer at DEF CON and Black Hat. Give a warm hand of applause to Mr. Stephen Ridley.
What's up, guys? How you doing? Can you hear me okay? Can everyone hear me? This is very impersonal for such a personal community. It's awfully distant. So I'm going to try to make this as personable as possible. So it's kind of thrown together. Just kidding. What I'll do here is I'll try to, basically, there's been a lot of stuff going on, so I'm going to give you a lot of material in a short amount of time, and kind of just tell you what we've been working on and some of the research we've been presenting about recently, and specifically some of the trainings we've been doing. So the talk, as he said, is Hardware Attacks, ARM Exploitation, and Android. And then I'll talk about a few other little side projects speckled here and there. There's a lot of photos, because with hardware stuff, it's tangible, and I can't show you a PCB up here on the podium, so I'm going to show you in slides and stuff. But first, I'd like to note that I don't see a single. Are there any black people in here? Are there any black people? Now, other than on the stage right now, can you please raise your hand? Nobody raised their hand. Wow. So maybe we need to start another community initiative, to reach out to, minorities, and yeah. Cool. I appreciate your pandering applause. That was quite nice of you. All right, so let's get down to business. I'm Stephen Ridley. @Stephen is me. So normally, what I would do in smaller circumstances, we run a blog called Don't Stuff Beans Up Your Nose, me and a former colleague, Stephen Lawler, and we would throw these condoms into the audience. And this place is too big to throw a bunch of condoms into the audience. But on the condoms, you can see they say, prevent more white hats, wear this black hat, and the condom is, of course, a black hat. If you want a couple of them, come see me. Just grab me. I'm the black guy at this conference. You'll be able to find me. All right, so all race issues aside, let's have a little fun with hardware and stuff. So first, a bit about me. I run a blog with Stephen Lawler, as I mentioned. Don'tStuffBeansUpYourNose.com. If you want to know the story behind that, I won't bore you. But it's a pretty neat story. We used to work together. There's a little bit about me. This screen is huge. It's huge. It's ridiculous. I've never seen a screen this big. What's that? It's right in front of me? Holy crap, right there. Look at that. On my laptop. Right there, too. There's a TV there, and there's one there, too. Thank you, whoever you are. You are a genius. All right, so who we are. I'm not crazy. I'm actually representing my buddy Stephen Lawler, who is right there. It's us drinking, and yes, that's a gift. That's how Stephen does Tokyo. That's at the Gundam Cafe, so nerd points there, I'll have you know. Anyway, so who we are. I run a small information security consultancy called Accipiter. Prior to that, I was the chief information security officer at Simple. I worked at McAfee. I founded the security architecture group there. I was a founding member of Kinshoto. We won a bunch of CTFs. Then we started running it at DEF CON. I've spoken at a bunch of places, DEF CON, Black Hat, now CCC, which is quite the honor, I might add. And so guest lectured places. And so we have a book coming out too, Android Hacker's Handbook. It's already available on Amazon, pre-order. A bunch of people smarter than I am, Colin Mulliner, Joshua Drake, and stuff like that, were gracious enough to have me help them out with the book. So check that out. It's really going to be good. And some of the stuff that we'll talk about in the book, there's really a cool hardware section, which I helped out with. I'll talk about some of those techniques in this talk. So Stephen Lawler is a buddy of mine. We used to work together, just paying homage to him. We do the Black Hat trainings together. So in this talk, what I'll do is I'll talk a little bit about how I discovered hardware hacking. I'm traditionally a software guy. I did a talk at Recon in 2011 called Hardware Hacking for Software People. And that talk seemed to really strike a chord with people in our community who are traditionally software people and need kind of a foothold into discovering hardware. And I know there's a lot of really smart hardware folks here. But for those of you who are like me, it's a really good introduction to some of these concepts. Then I'll talk a little bit about practical ARM exploitation, which is the course we've been teaching. And then I'll talk about how we built our development environments for ARM, which is also a barrier to entry for people who are trying to do mobile exploitation and transition their skills to the mobile environment. I'll talk a little bit about some interesting stuff from the course, specifically ROP on the ARM platform. Some of the neat stuff like stack flipping we might have to skip through. And then there's some really interesting side projects that I mentioned earlier. So this is kind of how did this all get started? I was a software guy. I specialized in exploitation and reverse engineering software, but I was always really interested in hardware. I would see cool projects like this. I would read Hackaday, and I just really didn't have a way to get into it. So one of the first things I did was, and this is a little bit of stuff from the hardware hacking for software people talk, I was really interested or really fascinated to learn that a lot of PCBs and a lot of chips speak standard serial protocols like I2C, SPI. And that's kind of like how I got introduced to it, because I'd used like RS-232 and stuff like that, you know, connecting your Win modems and stuff to your old PC to dial BBSs and issuing AT commands. So that was accessible to me. But I was really surprised to find out how many embedded systems made use of a lot of these serial protocols. So, so once I learned that, I started finding these serial-enabled ICs in a lot of consumer hardware. So I found them in analog to digital converters, bus controllers. I'm sure you've heard about Charlie Miller and Chris Vilasek's car hacking stuff. Really great body of research there. Even though it is stunt hacking, it was they did some really cool work there. That wasn't necessarily serial, that was CAN. But again, we're just talking wireline protocols that you can intercept and look at the data and really have interesting results. So I focused on some of these like I2C and SPI, and I started finding this stuff in routers. One interesting bit too, some of you may already know, but VGA and HDMI cables have I2C pins, so there's actual serial pins inside of your VGA cables. So when you plug your monitor into your computer, there's a communication that happens over 2 designated pins, and that's all on I2C. And that stuff I was like, whoa, now this is stuff I can handle, you know, like this is serial data, and I found some debugging tools and stuff like that. This is serial data that we can use to do kind of high-level reverse engineering or wow. Who shook this up? One of you shook this up. Nice. That's right. Here we go. Cue Flight of the Bumblebee. All right. Is this going to explode too? Look at that. It's because I'm black, isn't it? All right. I see how y'all do it, Germany. All right, that's all right. Thank you. It's good. It's only a MacBook Pro. That's all right. All right. If I don't slip and fall, it'll be good. Thank you, sir. All righty. A big hand for that guy. Thank you for also shaking up the bottle in the first place. All right, so I found these interesting serial protocols down on these PCBs, and I started finding them in routers and stuff. And again, this is from Hardware Hacking for Software People, which is a talk you can still get the video of online. But the first thing I did was bust open my cable modem at home. And on my cable modem, and I set up this kind of little crappy rig, which I'll explain in a second. This is a Broadcom chipset. And all this little Broadcom, I found 4 exposed cables, like 4 exposed pins. So I used a bunch of techniques, which I go into detail in the other talk. An oscilloscope to identify the pins, and some basic pin reverse engineering techniques, which is basically just combinatorics and trial and error. And basically figured out that there was a UART waiting on those pins, or a serial console. And from that, I could watch the thing boot. So it's an ECOS real-time operating system. And then, so once we got a little logs of it booting, we did a little fuzzing, and then we got a crash. So there's a built-in HTTP server running embedded on the Broadcom for doing landing pages and things like that, or like internal redirections that the service provider would do on your modem, like configure it this way, blah, blah, blah. So it was running this really crappy modem, and we made a GET request with a really ridiculously long request string, and it crashed. And so this isn't ARM per se, it's MIPS, but this was my first foray into hardware hacking, or software hacking enabled by hardware techniques. And so this is familiar territory, right? I have a debug console, presumably a debug console. I got a crash. Now what do I do next? So this is kind of the impetus for all of this, the last few years of research. So what we did was, now that we know that this is possible, we can do things like fuzz hardware devices, we can find crashes. Now we need to start really learning about how embedded systems work. So we looked around a little bit. We didn't focus on MIPS. We chose ARM. So we wanted to first set up our lab environment. So we messed around a little bit, and we set up a QEMU ARM environment. And QEMU is great to get started. It's really good because you can get comfortable with GDB and some of your GNU tool chains and things like that. You can start doing some assembly coding. You can write some basic shell code and test harnesses and test C programs. You can suck these binaries into IDA. You can start getting comfortable with ARM assembly and stuff like that. And what we started to do was exactly that. So we compiled the GNU ABI toolchain. We ran it on QEMU. We started basically writing our own. If you guys are old school like me, you'll remember Guerra's insecure programming examples. We basically did that for ARM. So we did stack overflows. We did some basic stuff where we'd have to do return to libc. We learned a lot about the protection mechanisms like XN, and all that kind of stuff. So we did this all in QEMU, all is well and good, and then we wanted to move to like real hardware. So we looked around for a little while for developer systems that would kind of do this, and at the time, the Raspberry Pi, whoops. I think I'm just gonna quit. You guys wanna just like grab a beer or something for the next 45 minutes? All right, there we go. So there's a lot of systems out there now, the Raspberry Pi, the Beagle board. Raspberry Pi, I think it was like a Kickstarter project or something at the time. It hadn't released yet. It was still kind of in its early stages. So we didn't use that. There's a few others out there, but eventually we looked around and we settled on the Gumsticks platform. And it's used a lot in like UAV systems, like temperature control systems. And it's basically just a small PC, the size of a gumstick, hence the name Gumsticks. And it runs on a micro SD card, and there's a bunch of pre-compiled Linux distributions and stuff for it. So we just started off using one of the suggested ones, using the Lenaro tool chain, but eventually we kind of spun up our own, and we got Linux running on these things. And so here's how they look. The Gumsticks board is pretty small, and it seats via mezzanine connectors into an expansion board. You can get different types of expansion boards for it to get Ethernet and all that kind of stuff. But the core board is really small, as you can see, compared to the rest of the stuff. So then we bought a bunch of these, and we called this the Lackluster Hack Cluster. So now what we've done is we've gone from a purely software emulated environment like QEMU to hardware, and we can start doing some of these exercises on hardware. Right. So what we did is by this time we had like a whole bunch of notes on ARM and all this other stuff, and so we decided, wait a minute, why don't we just give this to the community? Why don't we figure out how we can just bundle this stuff up and get people ramped up on ARM exploitation, and particularly owning mobiles. So we kind of built this into a steady progression like Guerra's insecure programming examples. And so we started distributing some of these exercises to people, kind of handing them out as crack me's or or own me's and stuff like that. And the word got out, and then people started saying, why don't you just roll this into a training, do it at Black Hat? So we said, well, we'd probably do that, but we don't really have a lot of real-world exploitation experience. So we started doing a few contracts. So I did some stuff with some smart meters. We did embedded systems like point-of-sale systems, and specifically mobile devices. Android, some Windows 7, and some embedded Linux systems as well. So then now with that exploitation experience, what we did is, all right, now we have real-world exploitation experience, let's roll this into a real course, and that's what we did. So we built the practical ARM exploitation course. It's basically 3 to 5 days, 900 slides, blah, 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 and we teach you everything you need to know. So a bunch of people have taken it, and we did it at CanSec, it sold out in a week. We did it at Black Hat 2 years in a row, it sold out in a couple weeks. We've done private trainings. We did one in Tokyo. We did one at Switzerland. We did a workshop at Insomniac last year. But what does this all teach us? It teaches us that we're in the post-PC exploitation environment. Mobile devices, embedded systems are way more popular than the computer that you leave on your desk or on your couch, right? It's always with you. It's with your pocket. So we're in the post-PC threat environment. So these are just things to think about if we're just as users or consumers of the technology. This is really, there's an interest in this stuff. People want to know how to own mobiles. It's just something for you to think about. So the world is changing, as I mentioned. And now I'll tell you a few interesting bits from our ARM course. We did quite a bit of research on this stuff. And obviously the big thing that you're going to want to know how to do for exploitation is return-oriented programming. And for those of you who are unfamiliar, you need to do return-oriented programming to evade modern protection or exploitation protection mechanisms, such as XN, or on operating systems like iOS, code signing. You can't load binaries or execute binaries from another system. You have to use native code that already exists. So you need to figure out how to use bits of code that are already inside of the executable. For those of you who are unfamiliar with ROP and the concept of ROP, Dino Dizovi had a really great analogy that he came up with. I was living in New York at the time. We all used to hang out and we were having beers. And one of the girlfriends said, I think Brandon, Dr. Raid as he's known, was explaining ROP to the girls, to the girlfriends. And one of the girls said, oh, it's kind of like those old ransom letters. You remember like on the old Murder, She Wrote days? Like, you know, the bad guy didn't want his handwriting to be recognized, so he would snip small pieces of newspaper clippings and magazines together to create a ransom note. That's essentially what ROP is, using small bits of pieces of code to form a larger message or a larger functional executable that does something that you want. So those small snippets of code are called gadgets. They're small bits of executable assembly code that exist somewhere in the process space of an executable, in this case on ARM. And the idea is that if you can do clever things with these small bits of code, you can string them together to do something malicious or something useful to you as an attacker. So what we did is we built a Linux distribution for our course, and we settled on a specific version of libc, and then we went gadget hunting inside of libc. And I'll talk to you briefly about how we did some of that gadget hunting, but it's extremely boring, and I can see some of you are already glazing over. I'll go into a bit of how that's done, but if you want to learn more about it, there's plenty of stuff on the web. So essentially what we did is we searched through libc, we found a bunch of gadgets, and then we built a library for you to quickly build your ROP payloads from. So there's a bunch of different gadgets that we found, but this is an example of an interesting ROP gadget. This one lives down in libc, and this is on our Linux distribution at 918DC. And essentially this gadget, all it does is pop R0, R1, R2, R3, R12, and LR. So it removes those values off the stack, and then it branches to R12. And so for those of you who are unfamiliar with ROP, essentially all this instruction does is it removes things from the stack and loads them into registers, and then begins executing at one of the registers that it loads off the stack. So essentially what we're doing is we're just putting a bunch of values onto the stack through a Stack Overflow or something like that, and then using gadgets like this to call functions. And we call this gadget the function call gadget, and it's kind of the one that the entire course hinges around. So this is the kind of stuff that we teach in the course. How to go hunt for gadgets. We use it to call interesting functions like mprotect, change the page permissions, to circumvent certain exploitation protection mechanisms. We also use it to call functions like mmap and mcopy. And I would go into a lot more detail about this, but I have a bunch more slides to go into, and I don't want to bore you all. And again, this is just more stuff on ROP. If you want to check out these slides, we have them on don'tstuffbeansupyournose.com. The huge takeaway from ROP is that basically because you're piecing together small bits of usable code, or small bits of executable code to do a larger function, it becomes really convoluted. And so this is an example of us simply trying to move one value, R6, or the value inside of a register R6 to R1, without changing another register. And so just the act of moving one value between two registers, from one register to another, without changing another register, took 14 steps. And through methods of indirection, we had to write values into memory. We had to use techniques called staggered memory, where we write these values into memory and then load these bottom three values out of memory. It becomes really convoluted. And this is the challenge of ROP. And this is where the bar is for exploitation, specifically on ARM and mobile devices. That's the huge takeaway. So this is, again, some more ROP stuff. This is how we build ROP gadgets. And this is essentially a representation of the stack. If you start up on the top left, we have the address of a ROP gadget, which is that function call gadget, pop R0, R3, R12, LR, BX, LR. And these ROP payloads are essentially just addresses on the stack. That's all we're doing, is we're just putting addresses onto the stack and then somehow kicking off our ROP chain depending on what the nature of the vulnerability is. So it's hard, it's error prone, it's very difficult. So what we did for the course is we built a Python script which has the address, annotations about the ROP gadgets, and we built it all into a builder. So you just drop into the CLI and you can build your ROP payloads with a few simple commands. And we think this is very useful because it allows you to access the concepts without really digging into the details of how ROP works and stuff. And if you want to, you can. So a little bit about ARM. ARM has a few different instruction modes. And this is one of the key things that we also want people to take away from our talks and our research. ARM processors have two modes. They have ARM mode, which is a 32-bit instruction mode, and they have thumb mode, which is a 16-bit instruction mode. And they actually have a few other instruction modes. There's this old one called thumb EE, which has special instructions to enter small bits of code. But this mode of execution is specifically for processors to execute JITted code, code that's generated by JIT. There's also a deprecated instruction mode called Giselle, and that was ARM processors could actually execute native Java code, which is really scary, right? But they could do it for a little while. I think this was deprecated in ARM v7 or something like that. But these processors could do it. And it was a feature originally designed for old feature phones. If you remember, prior to smartphones, there was a lot of Java, J2ME, and stuff like that running on phones. So it was built into the processor that it could do this stuff. But the key takeaway that we want people to know is that even though ROP is hard, right, or ROP is not hard, it's indirect, and it takes a lot more work, we have these different instruction modes. We have ARM mode, we have thumb mode, you have these really bizarre instruction modes. And one of the interesting things about that, and remember ROP, the idea with ROP is that we're using bits of code that already are in the process we're trying to exploit. Well, we can use the fact that these processors have different instruction modes to actually find more ROP gadgets. So this is one of the examples of the course. So one of the gadgets we use is a pop R0, R2 PC. And what this does is it removes a value from the stack and puts it in R0, removes a value from the stack, puts it in R2, removes a value from the stack and puts it in PC. PC is like EIP on x86. It's the instruction pointer. It points to the next thing the processor is going to execute. So using that, we can actually redirect execution. We can pop a value out of R0, R2, And the key thing about R0 and R2 is that they're used as parameters to a function. So this is a really great gadget for calling a function. You pop R0, R2, and then tell it where to go by popping PC. So we've been using pop R0, R2 PC, but we don't see it anywhere in there in the disassembly, right? And the reason is, it's because we're disassembling in 32-bit ARM mode. If we disassemble if we take the same region of memory and we disassemble it starting at 3850C, we get FD F705BD. I don't know if you can see that between the two lines. And if we reinterpret that as thumb mode, we get a pop R0, R2 PC. So what happens is that where pieces of code are supposed to run as 32-bit code, we can, using a few tricks, tell the processor, execute this as a different instruction mode. Use the same instructions, but execute as a different instruction mode, and you can find extra gadgets. So this is a key thing about ARM. So on your mobile platforms, on your mobile devices, even though ROP is difficult, it's actually a little bit easier because these processors have different instruction modes. So we teach some other tricks also. Just basic stuff like when you're doing exploitation, places to write stuff, like really extra scratch space. This is a really cool technique, is using the deltas between sections in the executable. You can write there because nothing in the program will be addressed to places inside the delta between the pages. These are really specific techniques, but we go into them in great detail, and you can also learn about them by downloading the slide deck or checking out our talk. We also go into Stack Overflows and how to bypass XN. Basically, at the beginning of our course, you can know absolutely nothing about exploitation with a little bit of experience using Linux and Python and some assembly code, and by the end of the course, you'll be bypassing all the modern protection mechanisms on Linux. So we talk about stack pivots. This is, again, George Wachurski, who is also an author of the Android Hacker's Handbook, explained, we called them pivots, and he's German and he had an accent, he called them pivots. So we pay homage to him with this by calling this technique pivots. And this is a really interesting technique, and it's really simple, and people do it on x86 all the time if you're familiar with x86 exploitation. The idea is essentially to, if you have a ROP payload that you've built, and you want to, and it exists on the heap, how do you get the stack to point into the heap? And the idea is that you find an instruction that basically tells the stack pointer to point somewhere into the heap. And we call that pivoting. So that's just a technique to, again, evade some protection mechanisms. I'm going to flip through some of this stuff. Ignore the Bukak heap. That's what we call heap spray. For those exploiters in the audience, you'll appreciate that. I want to talk about some of the other stuff, so the hardware-specific stuff, skipping through the ARM exploitation stuff, which you can find out later. This is my company Exhibitor, and this is really kind of more of a slideshow. This is more of a memoir of some of the stuff I've been doing in the last year or so. And so one of the first things that I wanted to do was learn how to interface debuggers with hardware. I showed you the example where we're using UART to get stuff that was sent by the application, maybe like the UART was tied to std_error or something like that, and they were printing debug messages. But maybe we want a way to actually debug the processor. So of course, JTAG. Everyone says JTAG. JTAG this, JTAG that. And I was thinking, coming from the software world, oh, JTAG must just be a way to get, way to debug hardware. It's just going to be, let me plug GDB into a chip and watch what the chip's doing. I can read registers and do stuff like that. It's not a silver bullet. Every manufacturer, every chip, they do it a little bit different. And there's many different JTAG adapters, and each JTAG adapter needs to have, understand the wireline protocol and the serial protocol that's spoken over JTAG, which is another common misconception. People think JTAG is the debug mechanism. It's actually not. There's actually a small piece of the JTAG specification for debugging. But one of the first things that I realized is that there was this huge misconception about JTAG. So my first foray into this, I got something called the J-Link, which is a debugger, and I used it on this Stellaris ARM development kit, which you can get for about $90. it comes with a preloaded bare metal image, which means that there's no operating system, there's just a single executable running on the chip. And then you get these headers, and you can just literally plug the J-Link adapter into the hardware, and then it plugs in, the J-Link plugs in over USB to your computer, and then you can use GDB or their debugging interface to talk to the software. Again, this is another shot of the J-Link. This is another cool thing. Ralph Philip Weinman has a really awesome paper. It's actually one of my favorite papers right now on the baseband exploitation. I'm sure you guys have heard of it. If you haven't, definitely look up Ralph Philip Weinman. Anyway, in his paper at the very beginning, he talks about how he used an Android G1, and he was able to JTAG debug the baseband processor. Cell phones have two processors, application processor and baseband processor. So I found a Polish company called multicom.pl, and they made this special adapter that fit the Android G1, and it gave me JTAG access to the Android G1. You also will run into cases where you have, this is kind of like slideshow memoir stuff here. You'll get cases where you'll see a connector that you suspect probably has UART or JTAG or something like that on it, but you won't know how to get access to it. And this is an example. This is something called, this is from a specific project I worked on, where I had no idea how to interface with this thing. I knew for a fact it had JTAG. I knew for a fact there was probably going to be UART on it based on the way it was positioned next to the board, but I didn't know what kind of connector that was. And so this is the kind of stuff you do. You end up spending hours trolling manufacturers' parts lists and Googling serial numbers. And eventually I found this customized Molex part. It turns out these things are called mezzanine connectors. But this mezzanine connector is something called SMD. If you're not, does anyone know what SMD is? Yeah? It's called surface mount. So surface mount format is basically something that sticks onto a PCB, and it has like very small pins. It's basically meant to be machine assembled by something called a pick and place machine. It's a little robot that uses a file called a centroid that knows the coordinates of where things belong on a PCB. So the robot puts it down, applies a very minuscule amount of solder, and applies heat to it, and that's how circuits get bonded to PCBs. So this SMD here is a surface mount. It's not meant for guys with big clumsy hands like myself to interface with. So how was I going to get this Molex connector connected to that thing? So these are just some of the tricks you come up with. This is a smart board, and it's just a PCB made by some guy in like Wahoo, Nebraska or something. He just makes these little boards that are they're basically breakout boards for many different types of SMD components. And what you can do is attach your small component to the inner part of the board, and then you see there's these horizontal lines there. You can just attach the slightest bit of the tip of a soldering iron, and it'll liquefy everything in the same horizontal line. So you can place the chip that you want, touch your soldering iron over on the side, and it'll liquefy, and it'll bond the parts to the board. But then the nice thing is that those leads also connect out to jumpers, where you can then plug your pins in and start to do stuff. So in this one particular case, I had that unknown connector. I found the mating part, ordered it from Molex, bonded it to this smart board, and got something like that, and took lots of notes, and eventually had this huge monstrosity where I was able to connect. Underneath that is the mating connector, and on the other side I soldered headers, and from this I can go back into my J-Link, and in the end of the day I had a debug connection to this point-of-sale system. So these are just the kind of tricks you come up with. Hardware hacking is a lot of arts and crafts. It's a lot of stuff that you don't think is going to be applicable, but then at the end of the day, you get debugger access, command line debugger access, which is really awesome. So we can get debugger access to stuff we see. We see we can access UARTs and stuff like that. Now what? So maybe one of the things we want to do is pull the firmware out of a thing. And this was illuminating for me. I was working with an electrical engineer. I'd never pulled firmware from a device before. And he really kind of showed me the ropes. So you'll see some photos of him in here. So this guy Chris, we looked at the schematics for the board. The manufacturer was nice enough to give us schematics. And so we narrowed these pins down to the chips that we wanted to target. We found the traces we want. Sometimes you get these schematics on hardware reverse engineering products. Sometimes you don't. And when you don't, you got to pull the firmware. So how do you do it? So in this particular case, and this is a bit of information here about how this is done. Remember I said SMD components are bonded to the board with small bits of solder, right? And solder is just liquid metal, basically. Once you heat it up, it liquefies. So how do you get pieces like that off the board? Well, they have something called chip quick, and chip quick is basically an alloy also, but it has a higher melting temperature. And so what we did here is we melted this chip quick stuff onto the pins that attached the component to the board. And so what we can do is we can liquefy the hotter alloy or the stronger alloy. It transfers heat to the solder underneath, and because it has a higher liquefying temperature, it keeps the solder hotter longer, keeps it liquefied, and gives you enough time to pull the components away from the board. So we did that for this small NAND chip here, excuse me. And so now you see it, now you don't. You pull the chip off the board and it looks like this. You got to clean off the chip quick and the alloy. And this is Chris meticulously doing that with a soldering iron and a heat gun and something to straighten out the pins. And eventually you'll get something like that. So now we got the chip free, so what do we do? So I called Travis Goodspeed. I asked him, how can I read something from, is there a universal reader or a flash programmer or something? And he recommended a device called the Zeltec 5000. It's a pretty high ticket, high price item, but if you have a contract or something, you can justify the expense. And so what Chris did and I did was we got the right adapter cable or the adapter set for it, slotted the chip in, and it looks like so. We plugged it into the Zeltec. Zeltec immediately identified the chip as an STM32 ARM core, and now we're seeing the tie-in, right? We can do ARM exploitation, we're attacking an ARM core, now we're getting convergence, right? We're using these hardware techniques to attack embedded devices. So we're able to pull the firmware, and once we pull the firmware, we can suck this thing into IDA. Sometimes you'll get a bare metal image, like a single executable that's doing direct I/O on the pins. Sometimes you'll get many file system images, like a CramFS or something like that. Then you'll have to use something like binwalk to slice up the binary file and figure out what part is the file system, what part's the bootable image or the kernel. You're going to have to fight with IDA a lot, and there's a lot of how-tos out there for how to carve up certain executable types. And we're actually going to be releasing in 2014, this is kind of pre-information, a hardware hacking course where you'll pull firmware images, learn how to load them into IDA, and do some basic ARM exploitation on them. We're hoping to release that this year at Black Hat. If not at Black Hat, we'll definitely do it at one of the smaller community events. I'm doing that with a guy named Joe Fitzpatrick. He's a really awesome hardware hacker that spent about a decade at Intel. So keep your eye out for that. And it's real-world hardware hacking. We're going to introduce that course later this year. So what's some other stuff we might want to do? Let's build some hardware interfaces. So we had a device that spoke to 30-pin dot cable and iOS dot cable. And this is another one. So we found this device called a pod gizmo. You might have seen Stefan Esser's tweets about building these debug cables and things for iPhones and stuff. He used the pod gizmo. And it's basically just a 30-pin dot cable that gives you these headers. You get these breakout headers. And what you can do is take these pod gizmos if you have a receptacle or plug side. And in this one particular case, we just wanted to build a tap. So we connected the receptacle on one side, we connected the plug on the other side, and then we made a receptacle in between. And the idea is that we're going to be intercepting data on the bus. So we're going to be intercepting serial data across a 30-pin dot connector. You take meticulous notes when you're doing all this kinds of stuff. I'm pretty ghetto. I just use a continuity connector for a lot of this. It beeps if you connect two pins together. You can figure out if you have a direct connection. I'll come back to this in a minute because we're going to segue into talking about the face dancer in just a moment, which is Travis Goodspeed's awesome USB debugging tool. But some of the other stuff you might want to do is build custom power interfaces. What I do for this is just hack it together, basically, splice cables, and then I use this lab power supply, the BK Precision, which is a really nice low-cost lab power supply. Lets you vary the amperage and the voltage to specifically power devices. Sometimes you might be pulling components away. You want to individually power a small chip or something. The BK Precision is perfect for that. So I mentioned before that we're going to be sniffing stuff on the USB port. So Travis Goodspeed's device is awesome for, it does some sniffy type things, but it's really good for simulating traffic, like creating traffic, and in that way it's a unique tool. But the Beagle 5000, which is created by a company named Total Phase, which also created the CAN sniffers that Charlie Miller and Dino Dizovi use for the car hacking stuff. They create some really great debugging interfaces, and this is their full speed, this is two of their devices actually, a full speed USB device, USB sniffer. And essentially what it does is you plug a device into the front, you plug the thing the device was supposed to plug into also into the front there as the host, and then out the back end it gives you a cable that plugs into your computer, and then you use like their really custom Wireshark style interface to intercept traffic. Are we good on time? Yeah? Okay. All right. So I feel like I might be boring you a little bit here, so let's quickly jump forward and talk about how we can spy on these communications. So I mentioned before I built this custom device to tap into this specific piece of hardware. And in the hardware hacking for software people talk, I go into a little bit how you can use oscilloscopes and things like that to view some data. But I want to specifically talk about this USB sniffer so we can get on to talking about Travis's really cool tool. 15 minutes. All right. So this Total Phase device, it looks kind of like this. You remember we built the dock connector way back here. Right there. Right? So we built this really cool tap. We know there's going to be USB stuff across that cable. How do we listen to it? So we're going to use this device called the Total Phase, and we'll plug the Total Phase into our really hacked cable. And the great thing about the Total Phase device is that they have a breakout cable that comes with it. So you just plug it into their interface, and it breaks out into these little header pins, and you can, and when you plug it all in, you get a really, really great representation of what's happening on the USB bus. So we have ways to sniff, right? We have tools like the Total Phase. We have tools like the Phase Stancer. So we have ways to sniff and intercept the data. How do we attack the data? We also have the firmware image, right? We can debug the processor. Now let's start putting stuff into the device. So we've got like our J-Link connected there. We can use GDB through another tool I wrote called PFI, which is to port forward. So we can port forward and have GDB running and attacking and debugging the device. So we can build custom Python interfaces to generate traffic, but what device can we use to actually attack these things? So one of the great devices that we can use, this slide is a little out of order, I apologize, we can use the Phase Stancer. And I'll go into that in a second. But one of the key things that you get from attacking low-level devices is you get crashes, right? Like before, I told you I fuzzed the built-in HTTP server, and we got a crash on the UART. Well, if we can fuzz stuff like on the USB bus, we'll also get crashes. We'll be able to observe them through our debugging interfaces. And lots of devices will implement their own USB stacks and their own USB protocol extensions and things like that in bare hardware. And you can find a lot of really juicy bugs if you can just tool up enough with the hardware to begin investigating that attack surface. One specific, everything's iOS compatible now. Everyone wants to talk to an iPhone. So you get a lot of devices that will have their own implementation of the iOS stack. That STM32 chip that I showed you earlier when I got the J-Link interface and it said, hey, this is an STM32, the one we ripped the firmware out of. These devices too, these OEMs that create the devices will also build libraries to implement some of this stuff. So they implement their own USB stack. Sometimes they'll implement the iOS stack for you and give you libraries to use to do that. And this one manufacturer, in fact, does. They call it the IAP libraries. So this is the iOS C implementation that they recommend for the STM32 devices. So when you start fuzzing via USB, you're going to find crashes inside of their iOS, inside of their IAP libraries and stuff. So skipping forward, so how do we inject a lot of this stuff? How do we start beginning investigating USB devices? The de facto tool is Travis Goodspeed's Face Dancer. It was the Face Dancer 10, the Face Dancer 11. A bunch of community people contributed and made some modifications, and we got the Face Dancer 21. For the longest time, this required assembly. And if you're like me and you're new to hardware, assembly is basically a barrier to entry that's extremely hard to overcome, right? You just want to sit down, you're used to Python, you're used to debuggers, you want to just start using a tool. So, to address this for the community, we got the idea to start something called int3.cc. If you go to the website int3.cc, it's basically a community-driven web store for information security related tools. And the one we wanted to start with was the Face Dancer. And the basic idea is that my company Accipiter, and people who are working with me front the cost of manufacturing, assembly, shipping, and fulfillment. So if you come to me with a cool project and you need help getting it to the masses or getting it to conferences like CCC, we'll basically pay for manufacturing. And so what we did this with was the Face Dancer 21. You can buy them now. We'll have them shipped to you within a few days. And since we opened the store in July, we've sold hundreds of these things, mostly international from the US. Thank you. Thank you. So this is an example, slightly modified Face Dancer. This is an Accipiter modified Face Dancer 21. You can see Travis' name's still there, but it's basically the same device. This is the web store, int3.cc, and we've launched a few other simple products. This was one called the USB condom, and essentially it's a USB connection that has the data pins chopped off. So if you want to charge your cell phone without the fear of data syncing, you can use a USB condom. I made it mostly as a joke, to do free giveaways at conferences and talks and stuff, and there was a media frenzy around it. NBC picked it up, Wired, everyone picked the story up, and it was for sale on int3.cc. We got 1.2 million hits in the first weekend. The Verge, it was on Slash.Newsy and a bunch of places. And so there's another project, which is also in the talk description, that we're running out of time for, but it's a hardware device that we're also selling on int3, and we also hope to be community backed. We'll maybe launch a Kickstarter project for it later this year, and it's a device called the Osprey. And the idea is that Osprey is going to be a hardware device. It's basically Metasploit for hardware. So if you want to do bus pirate stuff, if you want to do glitching, you basically download a firmware image, flash it over USB, and buy the appropriate modules, and you can do whatever it is you're trying to do. So the Osprey is actually for researchers. This is a tool that I want to get in the hand of researchers within the next year or so. The idea is that if you know enough about the firmware or know enough about the device to help me develop firmware images for it, great. If not, and you just want to use the different firmware images, kind of like Metasploit, you can be just a user also. But the problem is that manufacturing costs are really high. And so the idea behind this, and we don't know if it's going to be successful yet, is to launch it as a consumer product. So the idea is that I want to create this product that's called Tally, and essentially the device is used to monitor your home. And so built into these boards is a small chip that's capable of speaking Zigbee and these low-power RF, which people like us can use to attack low-power RF networks. But functionally to most consumers, what this device is a way to monitor the world around them. So you can take a Tally device, you can hang it on your door, you can take a Tally device, you can put it in your dog kennel and it'll monitor the temperature, and all devices will communicate via Zigbee or Simplicity as it's being prototyped now. They'll speak RF to each other, monitor the world around them, and if any events occur, like if you want to know if someone came into your hotel room while you're out at a conference, you can hang a Tally sensor on the door and it'll log that information internally to an MMC card, which will then be either transmitted via Bluetooth or USB to your cell phone. And there's an app running on your cell phone that I've written for Android that receives all the log data from your Tally device. And the idea is that these will be really low cost, 20 bucks a sensor, you can expand your RF network, and then, if you're a researcher, you can begin using the different firmware images to do things like glitching or attacking low power RF networks and stuff. But to consumers, they think they're getting a consumer product, and for us, we have the consumers subsidize the research tool, right? So that's the dream, and hopefully later this year, if you follow, you can sign up on the website and help support the idea, and if you are interested in helping develop for it, that would be great too, but right now you can just sign up on the mailing list, and we'll probably launch the Kickstarter later this year or something, or we'll figure out a way to do it as a community, but right now I just want to use this as an opportunity to open a dialogue with folks like yourself. So Project Osprey, so what are some of the things we want to do? It's got onboard EEPROM and micro SD for storage. We can use it for attacking RF networks, or we can use it for RF capability. It's low cost, low power. We can do serial interface. It's got 2 FTDIs on it to speak serial to your computer. It's got an expandable mezzanine, which are those connectors along the side, and I manufacture a small breadboard, so you can do prototyping on the breadboard, slot it into the board, and then update the firmware image, and boom, you've got a whole new device. There's the device there, some closer pictures of it. You can see the mezzanine along the top, and these are the devices communicating with each other. It's also powered on consumer batteries, 2 AAA batteries, which is cool. There's it plugged into an Android device. And so that's the idea, that's the dream. Osprey is Osprey for us, the researchers, and it's tallied to the consumer market. And hopefully we can have them pay for really awesome research tools for us. Some other really cool side features, we can use this thing for kind of bus pirate functionality or a good FET style functionality, not to replace Travis's awesome tool, but we can use it for that kind of thing. We can do it for simple glitching attacks, attacking low power RF networks, and some other neat interfaces. It's got a tag connect programming interface, so we can plug our computers into it and debug it using a really cool debugging interface. Those are the mezzanine connectors I mentioned. Those are the 2 antennas. Oops, right there. Those are the 2 antennas. So there's one SMA connector, and there's one built-in what's called a ceramic antenna. So if you want to attach a stronger antenna, you can screw it into the board. If not, you can use the permanent ceramic that's on board. Those are 2 USB connectors. We got an FTDI. The newer version has 2 FTDIs on it. And that's basically it. And like I said, in terms of milestones, basically you want to figure out how to get this to the consumer market, maybe do a Kickstarter or something and start doing first production runs and getting these to people in our community to do kind of community-driven development, figure out ways that people want to use it, tool up the features around it, and then have the consumer subsidize it for us. So conclusions and takeaways. I know this is a lot of stuff. There's a lot of hardware embedded hacking tools and techniques, ARM exploitation. Basically what I want you to know is if I can figure out how to do this stuff without having known anything or gotten an EE degree, it's very accessible to you. If you're smart enough to write software, you're smart enough to learn about hardware, because hardware is simpler than software. And what's really great is that through community endeavors like CCC and things like that, we can all band together and start to really build some awesome tools. Didat Crack is an awesome example. The Face Dancer is a great example. And we're really stepping into a new world of really awesome embedded security and really custom embedded devices made by us, the community. And that's basically it. That's all I have. And these are some URLs you may want. And thank you very much for listening, and hopefully we can make it happen.
Stephen, thanks for the talk. We have some time for questions. Please try to not so much pile up, but line up behind the microphones. And while you do that, we have a question from our Signal Angel.
Yeah, maybe it's just a short one. So the chip where you used the chip quick on, why didn't you access the JTAG interface directly? Why did you solder it off?
Oh, in that case, can you hear me?
Yeah.
I don't know, where are you? Who's speaking?
Me, up here.
Ah, there you go. Hey. All right, yeah, in that particular case, there was no, usually they have things like test points on the PCB where you can like solder a header or something. They had nothing. There was this small PCB real estate. So there's nothing we could really connect to. We could have probably gone in through the top and like soldered pins individually, but it's the same game basically. You're manually soldering pins. It's just easy to pull it off. And you could sacrifice one board, weaponize an attack, and then use it on other things. Like if it's a mass consumer product, You just sacrifice one and use it to attack multiple. So.
Okay, thank you.
Yeah.
Okay, could you be a little bit more quiet while leaving and entering? It's hard to do a Q&A session with so much people talking. And there's a question at microphone 2, please.
Hello? Okay. So less a question, more of just a couple of suggestions from my own experience. In regards to what the gentleman was just saying about like why did you desolder and why didn't you just use a JTAG? And what you're talking about with JTAG, there's I was at a con a couple weeks ago, and the guy gave a presentation, I think called the JTagulator.
Yeah, that's awesome.
Which is like a bus pirate
it's awesome.
for JTAG. So definitely check that out. I've got one. It's awesome.
Yeah.
Also, the Zeltec 5000 is really expensive, and Adafruit sells a carrier. They don't have the software, they don't have the programmer, so it's just the carrier. Yeah. But it's like a carrier for the chips. Yeah. So and then it breaks it out onto like 0.1 pins. Yeah. So and that's like $50 instead of $1,500.
Yeah.
So and that was basically it. Thanks.
Cool. Yeah. No, the JTagulator is great. In the Android Hacker's Handbook, we have a little bit about the JTagulator. For those who are unfamiliar, JTagulator is basically a way to brute force debugging pins. So if you have a JTAG interface, it isn't identified with a silk screen, like you don't know what pins do what. You may have 5 or 6 or 7 or 8 pins sticking out of the board. What the JTagulator does is it lets you attach to all those pins, and then it does all the math, the combinatorics, and tests each pin and tells you, okay, that one is this, TDO, that one's TDI, that one's power, that one's plus 5 volts. So yes, the JTagulator is awesome, and it's Joe Grand's tool. It's a great tool. It's pink, but it's great. It's really cool.
Okay, for all those leaving the room right now, I would like to ask you to not only convert all chairs that have been used as a table now back to a chair, and please also take your trash with you. Are there any more questions?
All right.
No, so thanks a lot. Please take your trash with you when you are leaving.